All right, so where we left off last week, we were in the process of designing digital filters. The week before, we looked at the moving average filter, which, as we saw, was something that you can use as a sort of low quality, low pass filter. It's great for getting noise, sort of Gaussian noise, random noise out of signals when you're acquiring the data to process. And then last week, we spent some time discussing a particular type of filter called a finite impulse response filter, which were the ones that you needed if you had an application where you required distortionless transmission. And remember the sort of the mathematical behavior for distortionless transmission was that the phase of the signal would be not altered, or if it is altered, it's in a linear proportion to the frequency. So when you plot the magnitude and phase response of the filters, if you look at the phase is a straight line with a negative gradient on it. We went through the process. The particular version that we used to design the FIR filter was to take a perfect or an ideal low-pass filter. You got the impulse response, which was also the time response. You started with the frequency response. You got the time response, which unfortunately is an infinite response. You truncate that, and then from there we developed the filter. And we saw that the particular type of transfer functions that we were using was symmetrical transfer functions. So for the behavior that we were looking for, to get that linear phase, the transfer function had to be symmetrical. In other words, if it was you had a power of z, then z would go from right across, be symmetrical across some zero, some central value. All right, and then we looked at some designs, and then I put up a lecture where there were a couple of designs for you to actually go through and try. Today, now we're going to look at the other type of filter in this bracket, which is the infinite response filter. So those particular, as we said last time and the week before, most of these designs are based on some other filter, like an analog version, whose behavior we already know. The idea being that you're not going to reinvent the wheel. If you know something and it works and you've already gone through the process, then we can take that now and let's see how we can adapt that to what we need. So we already saw that there was a relationship between the Z domain and the S domain. And for those of you who reviewed it, the relationship is back in lecture 11. And that is that Z is equal to e to the S capital T. Of course, capital T is 1 over your sampling frequency. So we have that relationship. So let's see if it is possible to start with some design that we know in the S-plane and then make a substitution for Z. And there are two ways to do it. We're going to explore one of them today. Right, so infinite response filters are used when linear phase is not important. So in the previous application that we spoke about last week, linear phase was important in certain applications like audio, like video, places where the relationship of the components that make up the signals are important. If that is not an issue, if all you want to do basically is to get rid of unwanted stuff, unwanted content, and retain the magnitude of what you want, then you use the infinite response filters. They tend to give you a sharper cutoff, but at the expense of this phase behavior that we were talking about before. So you start with some analog prototype. Why? Because as I said before, it's well known, it's well documented, so you don't have to go and reinvent the wheel. And then we converted our digital design by doing some sort of analog to digital mapping. So we already saw that there's a relationship between the analog domain that we model in the S plane to the digital domain that we model in the Z plane. So if we can find a suitable mapping to connect one plane to the other, that should work. And then we do a little bit of a what we call a spectral transformation, which is to adjust it now to get the sort of frequency response that we want. And the note in green here applies also to the designs that we've done before, that all filters require us to sample. There must be a sampling frequency. And remember, whatever is the cutoff frequency for the filter, you must sample at least twice that. Practically, we go to about 4 times for generally for good results. All right, you don't go exactly to the Nyquist frequency of this because the performance is not optimal at that point. So here we have an example of an analog filter. This is a 5th order filter. This was the one part of it was shown in the previous lecture. So this is a fifth order Butterworth filter. The blue line, this here is the magnitude response, right? Which is, and you notice the cutoff frequency here at 70% amplitude, it's at 1 kilohertz. I'm sampling at 5 kilohertz for here. Butterworth, for those of you who are who have done or are doing network synthesis and so on, these are just types of transfer functions. They are particular types of transfer functions. Remember, the HS is a ratio of some numerator and denominator polynomials. Depending on how these the form of the numerator and denominator polynomials are, there are certain standard categories that exist. Butterworth is one of them. There's Chebyshev, right? They are elliptical, and a whole bunch of others. We're not interested in that. So, but just to let you know that the particular type that is created. So if you want to retry it at any point in time, you can go into, for instance, MATLAB and ask it to create a 5th order Butterworth filter for you using this cutoff and this sampling frequency. And then when you check the response, it's going to give you a response looking like this. This is the thing that is of note for us, this red line here. Notice that is a phase response. And notice that it's not linear at all. If it was linear, it would have been a nice straight line with a negative slope as we went from 0 hertz all the way up to, well, simply since the sampling frequency is 5 kilohertz, the highest plotting frequency that we're going to have here is 2 kilohertz, right? So that is that particular issue. And then look at the impulse response. Remember, this is an analog prototype. Look at the impulse response. At this point in time, it looks like it settles down. We're going here, and it probably settles down somewhere at around here, right? Which is it looks like 4.2 milliseconds. 4.2 milliseconds, right? Is that infinite? Well, it depends on the application that you're dealing with. Remember, this is a time delay. So whatever you pass through this filter, before it sort of settles down to its behavior, you have a time of 4.2 milliseconds elapsing. And at that, during that time as well, the digital filter would have produced a significant number of values up until that point, values that it can't really use. That is not what we want. So the design approach that we take, well, sorry, this is what the finite response filter, we were truncated at this point. The infinite response is now going on. So if that behavior is not an issue, if you can tolerate the fact that the response will go on for a while, in this case 4.2 milliseconds before it settles down and so on, then we go ahead and we will design the filter. Notice that the response of the filter is pretty good, right? It's fairly decent. You have a sharpish roll-off at the 1 kilohertz cutoff, and the stop band is fairly flat. The pass band is fairly flat. Ideal, of course, if you remember, ideal would have done this. Okay. The equivalent finite response filter, a 5th order finite response, and you could try this using the techniques that we spoke about last week, would give you a much shallower roll-off for the same order, but this line here would be absolutely straight, right? A straight negative slope line indicating the constant phase response. So let's see how we design the infinite response filters, therefore. The design approach is fairly straightforward. We choose some analog filter whose performance we know. In our case, I will give you them. So for any questions that you have to work with and so on, I will give you the actual analog filter to use. If you're doing this in a practical application, you are going to have to come up with a filter design yourself. All right. So it's going to be based on some design. Right. This is just a set of them that are around. Right. Then you approximate the behavior of that analog prototype in one of two ways. We match the time response, which is what we call invariant mapping or impulse invariant mapping, or we match the frequency response. Next time on Wednesday, we're going to look at that. And this one now uses something called a bilinear transform. Now, this is not something like the Laplace and the Z transform. It's not a transform where you take something and you're going to do some integration and so on. We're going to see how that works, but we'll talk about that on Wednesday. The particular one we are interested in today is the impulse invariant design. So you match a digital filter so that the response for a given input is matching what the analog device is doing, in this case, an impulse. And if you, and those of you who remember, if you recall, the impulse response is the transfer function of a system. Remember, that's how we defined it. Right? The transfer function of a system was a Laplace response of the Laplace transform of the impulse response. So if what I'm doing here is that if I have the transfer function, therefore, of an analog filter, I am going to match that transfer function in the digital domain. So it's a transfer function mapping. So the theory is that if the transfer functions map, then the frequency behavior should likewise map. All right? The transfer function is going to be a good match for that particular signal, but it may not match another input. Remember, we are doing an impulse response mapping. All right. So if you take, for instance, after you've done the mapping and you have your answer, if you were to compare, for instance, the step response of the transfer functions, they're not going to match. All right. But that's not what we want. We know what we're interested in is an impulse response match so that we create a transfer function that is the same as the analog behavior that we had before. So what is the approach? Well, we start off with our inputs. Remember, HS is X. HS is XS, YS over XS. We take the input, whatever that input is, and we sample it. So we get XN. And from XN, we are able to get XZ. From XT, we are also able to get XS. And then from that, now we have YS is equal to XS and HS. HS is the analog prototype that we're going to get from somewhere. From this now, if I know YS, I can get YT. Then from YT, I could get YN. Then from YN, of course, I get YZ. So now I have both XZ and YZ. So therefore, I can get the transfer function that I want. Right? So this is how I'm going to move from HS to HZ. Now it is even simpler. This is just a flow chart, but remember, it is impulse response mapping. So XT is delta T. So if XT is delta T, then XZ is 1 and XS is also 1. So in other words, what we're looking for, we already have about half of the work done because we're saying it's an impulse response. And if that is the case, then all I need, if this is 1, then all I need to do is to go from HS to HZ. Everybody following? Make sense? Let me know, give me some feedback. I know it's early on a Monday morning. Making sense? Yes, no? Should I repeat it? All right. So how do I get, if I were to give you a simple problem and ask you, okay, if I give you HS, how do you get HZ? Well, from HS, let me just use a different color here. The process, if I were to give you this as a little math problem or a signals problem, HS, from HS, you have to have HT. So from HS, you need to do an inverse transform to get HT. Then from HT, you need to sample to get HNT. Of course, you need to know what T is. T is 1 over Fs, which has to be given somewhere. Remember, it's either given or you choose it depending on the requirement. And then once you get HNT, you go to your tables now and you get HZ. All right. As we said, XS and XZ are both 1 because we're dealing with an impulse response matching. So the problem really is about finding an inverse transform, sampling, and then finding a forward transform. Okay, which is why we did a little review of Z transforms and so on in those lectures a couple of weeks ago. So let's see how this works with a simple example. Here is a very simple first order filter. HS is 1 over S plus 1. A first order filter, this was the kind of thing that we did when we were doing Bode plots, right? So if you look at this, this is a low pass filter, simple slope, decaying at 20 dB per decade, etc., etc. And I'm telling you to use a sampling period of 1 second so that Fs is also 1 Hertz, therefore. Right? Very, very basic problem. So how do I get from HS to HZ? Remember, that's the issue. We know XS, I'm just reviewing, XS is 1 because it's an impulse invariant technique that we're using. So XT is delta T, XS is 1. YS, if I give you HS, is that YS is therefore 1 over S plus 1. So what is YT? The inverse transform of that. You go and look up from tables or you remember, I mean, this is a fairly straightforward one. You should have this in your mind. E to the minus T. And we put this here, the UT, to make sure the response is causal. Right? So you always, for correctness sake, if you don't have this and you just said e to the minus T, then in theory, you can have times before T equal to 0, which is not what we are about. So Yn, right, is you sample it, is e to, so you're taking T, remember you're getting this by replacing T with NT, N capital T, or N capital TS. We know this is 1, this was given. So Yn is going to be e to the N capital TS, UNTS. So I could get YZ. From your transform tables, this is in the form of an exponent, a to the N UNT. So the Z transform of that is 1 over 1 minus A Z minus 1. Make the substitutions, and we have YZ is that. We know that XZ is 1, as we said before. So therefore, the final transfer function is 1 over 1 minus that factor by Z to the minus 1. Of course, when you do this now, next step is to plot the spectrum and see what it looks like. whenever you do the design, the design has to match some issue that you were trying to solve, some response. So at that point, you must do a double check. So H omega, you're trying to plot H omega now, and remember Z, you're substituting Z equal e to the j capital omega here, and you run omega from 0 to pi, right? You could do it here, or you could put the values into MATLAB as we spoke about, and you could have it plot. So if you do that, this is what the frequency response, well, let's compare them now. HS, this was the frequency response of HS, the first order system. Notice it's there, it's a normal, well, we're just normalizing the frequency response here. So this was the original analog response. The phase response, well, it's a first order system. So the phase response for the analog prototype is fairly linear, right? It doesn't have too many, it just has one pole in it. So it's not going to distort anything to speak about. Let's look at what HZ. So this is HS. Look at HZ, the blue line. So the blue line is the frequency response, right, which is supposed to match this. I'll put both of them on the same chart in a little while. But of more significance to us, look at the difference in the phase response here. Look at this compared to what took place before. As you can see, the IIR, remember this is an infinite impulse response filter. This definitely does not have linear phase behavior at all. Notice that sort of behavior. So if you were to run something like an audio signal through this, you're going to get great distortion coming out. Right? This is not the type of filter that you're going to use for that application. But look at the impulse responses. Remember what we did is a transfer function mapping. We're mapping the impulse response for HS to the impulse response for HZ. So if you look at these two charts side by side, the one on the left is a continuous time domain, the one on the right is a discrete. And look at the sampling points here. And you will notice that the impulse responses match. If you take the point for point, the points here, right? The point here at 1 second, the value is about, what, about 3.5. At 1 second, look, about 3.5 here. At 2 seconds, right, it's something just below 1.5 here. 2 seconds, something just below 1.5. At 3, you're somewhere at about 0.5, and so on. The impulse response is in fact matching. So we've proven the point that the transfer functions match, which means that the impulse response matches. But there are some issues with it. If you look carefully at this, look at this response. This is the analog response. Look at the frequency response part of it. On this figure, you also have these slides available. So I wanted to check that. I wanted to check the response on figure 13 or slide 13 and the blue line on slide 14. And tell me what you observe. Have a look at it and tell me what is the most obvious, not about the shape, but there's something very obvious about the difference between the magnitude or the frequency response on slide 13, which is the analog one, and on slide 14. Have a look at the images and see if you can tell me what that difference is. Anybody know? Anybody seeing what the difference is? What's the magnitude of DC for the analog? What's the magnitude of DC for the analog filter? . If you look carefully, you would see that the magnitude of DC for the analog filter is 1. In the case of the digital filter, the magnitude at DC is 1.6. So we have to do a little bit of scaling here. Right? If you were to look at it, right, the impulse response match between the two of them, but there's a little scaling that we're going to have to do there, and we'll talk about that in a second. So first off, in order for this to work, remember the whole process is that you've given some HS, and along the way, you have to convert that HS to some HZ. Right? So that, of course, requires that HS can be expressed in some form that you can find an inverse transform, because what you're doing is you're going HS to HT to HNT to HZ. So once you're given the HS now, you have to get it in some form that you could find the inverse transform. So you have to be able to put it into things like partial fractions. In partial fraction forms, you can do that. Once the analog version is stable, which is not too much here, but it controls people. If you're doing transform matching in controls, right? Once you know that if the analog version is stable, meaning that the poles are all in the left-hand side, remember that the poles in the left-hand side of the S-plane map inside a unit circle, which is stable. So if you have a stable analog prototype, the discrete prototype is going to be stable, all right? Not something for us to be too worried here, but if you're doing advanced controls or digital controls and so on, they do something very similar to this. And they also prove that once you have a stable analog transfer function, then the discrete transfer function should be stable as well, okay, because of the position of the poles mapping from the S to the Z plane. Remember this, right? You must always sample at least twice the bandwidth of the filter to avoid sampling, to avoid aliasing, sorry. And we saw this. What about the amplitudes? Well, we have to scale the amplitude of the digital filter is 1.6 times the amplitude at 0 of the DC filter. So we have to scale it by 1. We have to take the discrete time, H, Z, and multiply by 1 over 1.6 to get the amplitude back at 1 at DC, right? So that is the original one. And here are the two responses on the same graph. So the red one is the analog prototype that we started off with. The blue is the impulse response matched answer. And the green one is when we scale it so that the responses are DC match. Okay? Notice that the behavior is a little bit questionable. All right? But of course, it's a very simple filter that we started off to use an example. We're going to use a slightly more complicated one in a short while, just to see how it works. Everybody following? All right. So what is the input-output difference equation for this? You remember, you just cross multiply. Remember, this is x, z over, sorry, yz is x, well, yeah, h is basically yz over x, sorry, yz over x. Right? So you could cross multiply, and very simply, this is the input-output difference equation. If you draw this out, remember we spent some time doing this, notice that this particular response has a past value of the output. This is the output yn here. So it also holds past outputs. In other words, there's feedback. Remember we said that the finite response filters Okay, there was just a question here. We may be required to do partial fractions in the exam then? Yes. Right? If you're designing one of these filters, yes, you have to be able to do partial fractions, right? Which is something that I mean, you should be accustomed doing that all the way through. It's not you did it here, you did it for the Laplace course, you did it for controls, you did it for signals. So by now, what I'm going to ask you to do is not complex thing, right? Any exam question is not to see if you can do if you can do complicated partial fractions. It's not a test of partial fractions. It will be a test on if you can do a filter design, which happens to require that. Okay. Right. So as we were saying, the FIR filters, like what we did last week, no feedback. Right? The IIR have feedback. And the feedback, as we said some time ago and a couple of lectures back, the feedback is what gives it the infinite response, because it is taking the past outputs and reusing them in, the response tends to go on a lot more. The finite response filters only take the input. So as soon as the input sequence or whatever it is ends, the answers end shortly after that. In the case of an infinite response filters, once the input data ends, you still have a set of stored output values that have to be processed. So the response goes on, right? How long it goes on depends on the particular filter that you're dealing with. And we had this some time back that they find the infinite response filters therefore have both feed forward and feedback parts to them. Remember this form of it, the feed forward parts, okay, are the B coefficients here. So the finite response filters, like what we did last week, the finite response filters only have, FIR filters only have these coefficients, the B coefficients. The infinite response filters have both the A and the B coefficients. These are the feedback ones here, okay? Right, so let's look at a slightly more complicated one, and this is the one where, yes, we will kind of look at that if you had to do partial fractions for this. So here's a design. Again, you're given it, whether it's good, bad, or indifferent. I don't know, we could care less. You're given this, and you want to get HZ. So the mapping, again, is HS to HT to HNT to HZ. So HS to HT, this is the inverse Laplace transform here. Right, and this, as Russell was asking, this is partial fractions here. So if you look at HS now, you express HS, you look at this, first off, you're going to see if this could factorize or not, right? If it can factor, if it's simple, once the poles are not complicated, and people forget too that sometimes you could do it by inspection. So you could watch this and say, okay, this is S plus, this was really, S plus 4 into S plus 1, right? Sometimes it's not so obvious. And if that is the case, then remember your quadratic formula. And there's nothing wrong with having S plus 4.77 into S plus 3.62 for argument's sake, right? And working the partial fractions for that. This is just theoretical, all right? If it turns out to be, well, first off, this now, if you get rid of this here. Right. So if it's easy to do by inspection, it's A over this plus B over They're simple root. Remember the same sort of things that you had before. If it's repeated roots and that kind of thing. As I said, it's unlikely that you will get a one that will take you more time to do the partial fraction than to design the filter, right? What we're doing here is a filter design. So it is complicated enough that I want to see, okay, you know how to go from HS to HT at least, and then go the next way forward. So once you solve here for the coefficients, right? So this is your partial fractions here. You go to your tables, right? You go to your tables because this is going to give me some, from the tables you get HT. And then from HT, you get HNT. Remember, T is 0.5 here. So where whatever you had inside of here, you replace with like the E's and that kind of thing. So this is 3 over, 3e to the minus 4t. So you replace the t with n 0.5 n. Okay. And then you substitute inside of here. So HZ, right? If you go, you will get HZ in this form, and then you get it into the more standard form, and then you simplify. You substitute for TS, which is 0.5, and you substitute. So if you substitute, remember this simply, the form that we want to get it, HZ is it our form looking like this, with descending coefficients of Z. When you go to your Z transform tables, sometimes after here, you will get the Z transform sometimes looking in this form. Remember, to get from here to here is simply a question of looking at this. If I multiply this through by Z minus 1 over Z minus 1, then I get it into this form on the left-hand side here. All right? All fairly simple manipulation. The idea, of course, is that once you get HZ now, you have to get it into the standard form. Okay? So when you're doing this in any issue, here's the answer here, so you can double check that. Once you're doing it, I expect you to at least try in any problem or in the exam, and you will see it in the past papers as well when we're doing that, to get it into this form, right? So your answer going to be here, and this first coefficient is 1. So it's 1. You remember, this is how the standard form is here, right? So you get it into that form for me, please, all right? Of course, if you're doing, as I keep mentioning before, if you're doing this, and typically this might be like, let's say a 10-point question and so on. If you reach to the stage where you simplify this, you get an answer, but you're not able to, the answer here when you do it, let's say the answer here had 12 plus something something. To get 1 here, it means that you have to divide the numerator and denominator by 12. If you're not able to do that and you leave the answer like this, and everything else is correct, you have 8 out of the 10 marks, all right? So once you're doing the exam or you're doing any question and the time runs out, if you're not able to simplify it, but everything else is correct up to that point, go on to the next question. Don't waste your time simplifying it at the expense of getting marks elsewhere, all right? So if you do this correctly, you should get the answer looking like this. Of course, in the exam, I wouldn't, or anywhere else, I wouldn't ask you to plot the magnitude and phase, but this is what that response looks like, right? So the filter actually looks like some form, this is more like a high-pass filter, the blue line. Look at the phase. So you can see clearly this is an infinite response filter. The phase is horrible. You're not going to use it for any application where phase is something that you want. Okay, look at the impulse response, though. We're matching impulse responses. So look at the HT on top and the HNT on the bottom right. So the top left and the bottom right. And again, if you look at them and you match them point for point, you will see that the impulse response mapping matched, right? What we have done in here is to do transfer function mapping. Okay. And of course, if you were to plot it out, remember the transfer function is b naught plus b1 z minus 1 plus over 1 plus a naught z minus 1 plus a1 z minus 2, etc. Okay, so you look at that, and therefore, if I were to draw the block diagram out for it, right, you have both b and a coefficients inside of here. Right, review the section to remember what canonical was. Remember, there's another version called direct form, right, which is back in lecture 14, I believe it was, right? The different types of representation. This is how it is actually implemented if you were to program this into, this is how the data flow would actually go. All right. So questions. Remember, the essence of this is that you're taking, we are mapping, it's an impulse response, impulse invariant mapping. So the idea is, if it's impulse invariant, means the input is xt is an impulse. So what we're basically trying to match is hs, and we're trying to match that to hz, right? A transfer function mapping, in other words. And the steps are, of course, to go from hs to ht. Yes, you have to do the partial fractions and so on. And then from ht, you sample, you know what ts is, so that gives you hnts. And from hnts now, we go and we can get hz. You have transform tables here, so you don't have to remember or the transform tables. I give you that. So if even you forget the simplest of z or Laplace transforms, you just have to look it up in the back. Okay, what you have to do is to remember how to do, as Russell was asking here, how to do what do you call it? Partial fractions, simple partial fractions. Okay, right? And even in the Laplace tables in the back, if you may forget that too, there are versions that you could go. For instance, you could have looked up this one. If you forgot how to do partial fractions, there is in the Laplace tables, there are right at the bottom, this one, where you can look up this, and I think they have it in the form of like es plus f over s squared plus as plus b, some kind of thing like that. And there's a value for each of the coefficients, ef. You just have to substitute from what you have here. So if you absolutely forgot, for instance, in this example, how to do a partial fraction, which I really believe that you shouldn't have to do it, that you could do, you could look it up straight in the table and so on. All right. So everybody all right with that? We covered a bit. It's fairly straightforward. Remember, the whole issue behind this particular type, there's another type that we're going to speak about on Wednesday, but the impulse invariant mapping is a transfer function mapping. So you're starting with an hs and you're going to get an hz. And there are two steps: the inverse transform, sampling, and then the forward transform. Okay? Make sense? Yeah? Right. So as I put in the chat, to sort of facilitate the people who under stress, last minute stress with their 30-20 projects and so on, we will be having the next couple of Wednesday classes will be online as well. All right, so we can follow it. They will be recorded too. Still try to attend, but if you can't for whatever reason, because of the final year project, if you can't attend, the lecture is going to be recorded, so it will be available. All right, so let's get through those. On Wednesday, we're going to look at the other type of well, first off, we're going to run through some examples here with using the infinite response technique, and then look at the other type of approach to take. And then the following week, we're going to look at some applications of signal processing. We're almost at the end of the material act. Okay, problem set 3 is up as well, so you could start having a look at that too, to sort of cover some of the last sets of topics that we did. All right. So any questions here before I close off this morning? All right. Okay, so I'll stop the recording here.